Hello, everyone. So this is the second part of this week session, and today we'll talk about generating set and basis. So let's start. First of all, what is generating set? We talked about some spaces and subspaces, and the example of a subspace can be if we are in R2, can be, let's say, a line which goes through point 0. And if we take any vector on this line, so let's say some vector A, then we know that any other vector, let's say vector B, any other vector B can be written as some number times the vector A for some real number. And of course, we can do this for any vector B. So this means for any vector B, we can find some number such that B is equal to lambda A. In fact, any vector on this line can be written in terms of this vector A. So this vector A must be fixed. And then it is called, we can say that the line, let's call it, let's say L, is generated by this vector A. Since any vector on this line can be written in terms of A, this line is generated by this vector A. Or we can say that the line L is generating set by this vector A. Similarly, if we, let's say, want to generate a plane, let's say we look at the plane, which is the plane of this board. So let's take here, let's say, vector C and vector D. We know that whatever vector on this plane we take, let's say vector X, X can be written in terms of C and D. So again, we must multiply by some numbers and add. So we should write a linear combination of this vector C and D. Let's say lambda C plus mu D. So we can say that for any X which is on the plane, the run numbers lambda and mu, real numbers, such that this our vector X can be written in terms of C and D as their linear combination. So in this case, we can say that these two vectors C and D generate this plane. Right? So this is the meaning of generating set. And of course, we can talk about generating set in general. Let's write a general definition for this generating set. So the definition is the following. First of all, let me add here something. So generating set, in fact, the set of vectors by which we generate some plane or line. For example, here, the generating set is vector A, is generating set. So in general, generating set is the set of vectors or the set of elements of a vector space. So if we look at the vector space, let's say this one, then the set of elements from the vector space, let's say V1 and so on, Vm, this is of course elements of this vector space, is called generating set let's say of V if any other V from V can be written as linear combination. Let's say some, let me use maybe just lambda 1 v1 plus lambda 2 v2 plus so on plus lambda m vm. So if for any vector v you can find some numbers, lambda 1 and so on lambda m, such that the linear combination of these numbers with these elements of our set give you precisely vector v. Okay, so this is the definition of generating set. And in this case, if we have it, we write that V is span of V1 and so on Vm. So span means that any vector from this is a linear combination of these m vectors. Okay. And in fact, it's always when we span some using some vectors, we always get a subspace. For example, let's look at span. Let's say 1, 0, 1, and maybe 1, 0, 0. This will be subspace in R3. Why this is a subspace? First of all, because when you span, you add all the linear combinations. So this means that the summation and multiplication by numbers, they are well defined inside of thing that you get, right? Next, what else do we need? We need, for example, 0 element, right? Which we get when we take lambdas, all lambdas zeros. It's possible. And so 0 vector is inside. And so on, all the properties will work. So all things can be checked for being a subspace. So whatever vector you take, if you construct a span of them, you will always get a subspace. Okay, what else is important? And now let's talk about basis. What is the difference between basis and generating set? You already know this word basis, and for example, you know that, let's say, basis of R2 is 1, 0, 2 vectors, 0, 1, right? We call it standard vector basis, which is also orthonormal. So we know that this is basis. This is also a generating set of R2. This is also generating set of R2. Why it is so? Because whatever vector from R2 you take, you can write it as linear combination of these two vectors, right? So in fact, any basis is also a generating set. But not any generating set is basis. For example, let's look at set, let's say 1, 0, 1, 1, 0, 0, and let's say 3, 0, 0. Let's look at the span of this. Let's look at the span of this, and if you span it, in fact, this will be a subspace in R3, right? And if you span it, in fact, you will get the same. You will get the same as span of 1, 0, 1, 1, 0, 0. Why it is so? Because these two vectors are linearly dependent. One vector is just multiple of the other. So this vector is inside here because this is 3 times 1, 0, 0, right? So this is generating set, and in fact, this is a basis. What is the difference So let me write it here so that this one 0, 0 is generating set, but not a basis. The basis is set of vectors which must be linearly independent. So in fact, this is the smallest set of vectors by which you can generate particular subspace or a space. So definition of the basis, let's say basis, we can write many definitions, but let's use this one, for example, is a minimal generating set of a space or subspace. Again, what does it mean, minimal? Minimal, it means that you cannot remove any vector from this set of vectors. So you cannot remove, or if you remove any vector from the set, from the basis, you will not get this space. What does it mean? For example, we looked at this example here. We just removed this vector and we still have the same subspace in R3, right? So this is not a basis. But here, if you remove one of these two vectors, you will not get the same span. This particular span is a plane in R3, but if you remove one of these vectors, you will get only a line in R3, okay? So this is the meaning of this minimal. So they explain this minimal in the sense that so there is no smaller set that span V. So minimal also means that there is no smaller set that span V. Okay. Are there any questions here? Maybe comments?
No questions.
Okay. And in fact, there are plenty kind of equivalent definitions of a basis. I think you should know all of them. So basis is crucially important because when you know basis of the vector space, of course, you know all the structure of the space. So first of all, let's call maybe B to be basis. So, and the following things are equivalent. B is basis of V. B is, so just the definition which I just gave you is a minimal generating set. Next one, that B is the maximal linearly independent set. B is a maximal linearly independent set of V. So what does it mean, maximal linearly independent? You cannot find one more vector from V which would be linearly independent with the vectors which are already in the basis. Okay, so let's look now at this example. Whatever vector you take from this span, this will be always linearly dependent with these two vectors. So this is the meaning. Okay, and the last one, which is just again from the definition of generating set, every vector V from V is a linear combination of vectors from B and so of vectors from B, that is V can be written as, let's say, sum of lambda IVI. And what is important, this is, in fact, this is a definition of generating set, but what should we add to make it a basis? Every V is a linear combination of vectors from B, and this linear combination is unique. So we can add here to make it basis is a unique linear combination, right? So if we, for example, let's again look at R2 and let's consider 3 vectors. Let's say we look at this plane of the board. Let's consider some arbitrary 3 vectors. Of course, we know that whatever vector x we take, x can be written, so this is an example, x can be written as, let's say, lambda A mu B plus maybe nu C, right? It's possible, but we can also write it as maybe some alpha A plus beta B without using C. Or we can write it as, let's say, which letters we have? Gamma C plus delta B. It's also possible. So these 3 vectors are linearly dependent. It's not a basis, right? This is not a basis. It's generating set and they are linearly dependent. Therefore, there are plenty of ways to write arbitrary vector as their linear combination. But if this is a basis, then such linear combination is unique because 2 vectors are linearly independent, right? And it's not possible to find another way. You can write it, you can prove it algebraically. So basis is unique, not basis, sorry. This is wrong. Linear combination is unique if B is basis. Assume that some vector V has, let's say, 2 linear combinations. Maybe mu. Okay, assume that vector V from capital V, assume that you can find 2 linear combinations for this, for one vector. What this means then? This means that from this equality, you can move one, let's say this sum to the left side, and this will be just sum I from 1 to m lambda I minus mu I vi is equal to 0, right? Is this step clear?
Yes.
Okay, and this is 0 and vi, they are all, since this is a basis, all vi are linearly independent, right? Linearly independent. So from the definition of linearly independence, if we have that linear combination of them is 0, we must get that all of them are zeros. All of the coefficients are zeros, right?
Yes.
For all I. So this means that for all I, the number is just equal, right? This means that these 2 linear combinations just coincide because the numbers are just equal, right? So this means that such linear combination is unique. So this is another important difference between basis and generating set. From generating set, for just one vector, you can combine plenty of linear combinations, if it's not a basis, of course. If it's a basis, then only one linear combination for one vector exists, okay? Let's maybe, are there any questions about this part?
No questions.
Okay, now another question. For example, we have some vector space. Is the basis for this vector space unique? Of course, no, right?
Yes. Yeah. No.
It's not unique. Why? Because there are plenty of vectors in the vector space of set of vectors which are linearly independent. What is the basis? For example, if we are, let's say, in R2, to find a basis, it's enough just to find two linearly independent vectors, right?
Yeah.
So, for example, our standard basis, they are linearly independent. Another example, let's say, this couple of vectors, they are also linearly independent. And we can find plenty of them, in fact, infinitely many. And similarly for any vector space, you can find infinitely many bases for arbitrary vector space. Okay?
Okay.
Okay, let's look at what else do we have. It's important also to be able to find a basis or determine that some set of vectors is basis or not. So how to, let's say, determine that B is a basis. There is quite a simple way. We just construct, for example, let's look at, I just want to find an example. Let's consider a generating set. Let's call it A. One, two, three, four. 2 minus 1, 0, 2. And 1, 1, 0, minus 4. So this is generating set. So this means that we look at, why do they use different definitions? Okay, let's maybe add span here. Here is span. So we take this vector and we take all possible linear combinations. And the question, what is the basis of this vector space? So this is subspace, in fact, in R4, right? And the question, what is the basis? And since we know that this is generating set, this can be a basis, right? But can be not a basis. What is the difference? We must check if they are linearly independent or not. If they are linearly independent, then this is basis. If not, it's not a basis, right? So to check, so this will be a basis if and only if they are linearly independent. And remember, we already looked at the question how to check that vectors are linearly independent. We just construct a matrix with the columns. The columns are these vectors. And we row reduce it. So we leave the first one to remove these two. we must multiply the first row by -2 and add to the second row. So 0, -4, -1, -5, -2, -1, -1. To get rid of this 3, we must multiply the first row by -3 and add the third row. 0, -6, and -3. And finally, to get rid of this 4, we must multiply the first row by -4 and add the fourth row. So -8 plus this one -6 and -4 -8. Okay. What should we do next? 1, 0, 0, 0. What we have? 2, 1. Then we must write the second row. And we must get rid of this -6 and -6. So for this, we need to multiply R2 by -6 and add 5 R3, right? So this one definitely 0. So we must do this operation only with these two numbers. So R2 by -6, we get 6 minus 15, right? So we get -9. And the same for this last row, only R4 here. So we get 6 minus 40. So in fact, now it doesn't so matter, but anyway, -34. So what do we see? We see that all 3 columns are pivot columns, right? So in fact, we can remove this -34. So we can say that this is 1, 2, 1, -5, -1, 0, 0, -9, and for the last one doesn't matter. So all of them are pivot columns. So conclusion, linearly, the vectors are linearly independent. So conclusion that this is indeed a basis for this span.
If I'm not mistaken, we had the second method to determine basis linear independence.
Which one?
So, for example, we take the first vector, multiply by A plus B multiplied by second vector plus C multiplied by third vector, and solve the
and you will solve the system, right?
Yeah, system.
But you will get the matrix of the system like this, and anyway you'll have to row reduce. So you will do the same procedure as I just did. So the idea came from what you just said, okay?
Yeah.
Okay. Are there any more questions, maybe?
No questions.
Okay, what can we get from the basis? The very important number for a space and a subspace is its dimension. And if we talk from school, we used to call dimension to be, for example, if we are in R2, the dimension, okay, maybe let me write the dimension. So shortly, this is D. So dimension of R2, we say this is 2, right? Dimension of R, this is 1. Dimension of Rn, this is n, right? This is what we know. We also know that, for example, dimension of a line, let's say any line, is 1, right? Dimension of a line is 1. And why it is so? Why it is so? Because when we generate a line, it's enough to take only one vector to generate it. Therefore, dimension is 1. Dimension of a plane is 2, because for a plane, we need 2 vectors to generate it, right?
Yeah.
So what is in general dimension? Dimension of V is number of vectors in bases of V. Okay, so you need to find the basis. How many vectors you have? This will be this dimension. For example, in previous example, we have some subspace in R4. Its dimension, since this is a basis, its dimension is, in this case, dimension of A is 3, right? Because we have exactly 3 vectors in the basis. Okay. Is this clear?
Yeah, it's clear.
Let's then move on to rank. Rank of a matrix is very important notion. And in fact, when we studied linear algebra, I tried to maybe give for a rank about 3 or 4 lectures, because I tried to prove everything. But here I want just to give you a definition of a rank, and then we will list all the important properties of the rank without proof, okay? So what do we have here? For example, first of all, rank is defined for a matrix. Let's say A is a matrix. We write it as M times N, right? Sorry. And today in the book, they use rank of A. They use just RK of A. And what is the rank of A? The definition, the number of is the number of linearly independent columns of A. So this is definition. Rank is the number of linearly independent columns of A. So now we clearly see how to determine the rank. We take A, we row reduce it, and calculate the number of pivot columns, right? Okay, and what is important for A, for rank? First property is that if you transpose A, so in fact the columns becomes rows and the rows becomes columns, you will get another matrix, which we call A transpose. And if you calculate now the number of linearly independent columns, then you will get the same number as for A. So in fact, the rank of A is the same as the rank of A transposed. So this means that rank can be defined as a number of linearly independent columns or the number of linearly independent rows. These numbers are the same. So number of linearly independent columns is the same as the number of linearly independent rows. Okay. Another important property is that, so in fact, again, this comes easily from this fact. This is quite important theorem and it requires some proof, not a simple one. And definitely from this fact, we can get that if we take columns of A and we span, so columns of A, and we span, so we contract some subspace, right? That's denoted by U. And first of all, we can notice that this will be some subspace in Rm, right? Because the number of rows is m, so the columns will have m coordinates, right? Each column will have m coordinates. And what is the rank? The rank will be the rank of A will be just dimension of this U, right? So since the number of linearly independent columns of this A will be exactly the number of basis vectors, right?
Yeah.
So this is dimension. Similarly, we can talk about rows. About the columns, again, let me add here that this subspace, later we will call as image of A. And now if we take rows and we span another subspace, as denoted by W, this will be a subspace already in Rn, right? Because the vectors here will have n coordinates. And again, we get that the rank of A, since we know that the rank for columns and rows will be the same. So again, this will be dimension of this W. Right? So you see that these two subspaces, they have the same dimension, but it doesn't mean that the subspaces are the same. This can be completely different things, but they have the same dimension. Okay, it's also important to notice that, I hope you all remember this, that if we have n times n matrix, then A is invertible. It's also an important theorem if and only if the rank of A is exactly n, right? And connected to this, we can talk about the solution of corresponding system. So this means that, let's say, system, okay, let's maybe talk about again, back to A from Rmn, and let's say B from Rm. And then we'll look at the system Ax is equal to B, has a solution if the rank of A coincides with the rank of A. Together we add one more column B. So in fact, this matrix we call the augmented matrix for this matrix A, right? Okay, what else is important? Also, we can talk about a solution of homogeneous system, that is, we have 0 on the right. In fact, this will be later, this will be a subspace which is called the kernel. And a solution of this is subspace, some subspace. Again, it's important statement. You must be sure that indeed this is a subspace, because if, let's say, x1 and x2 are solutions, the sum is also solution, right?
Yeah.
Multiply by any number is also solution. 0 is solution, right? So this is a subspace. Solutions of this system is a subspace, and this subspace has dimension equal to n minus rank of A. This is again not simple but important statement. Okay, and I think about the rank, that's it. Maybe we'll just to remind, we will just solve one example to determine the rank. Finding rank. So assume that A is 1, 2, 1, minus 2, minus 3, 1, 3, 5, 0. Okay, so we, again, to find the rank, we need to row reduce. So we leave the first one, we multiply the first row by 2 and add the second row. We get 0. 4 minus 3 is 1. 2 plus 1 is 3. Then we multiply the first row by minus 3 and add the third row. So we get 0. Minus 6 plus 5 minus 1, and minus 3 plus 0 minus 3. 1, 2, 1, 0, 1, 3. Then we need to get rid of this minus 1, right? We need to get 0, 0. So we just add R2 and R3, and we see that we have also 0 here, right? So in this case, we have 2 pivot columns. So the conclusion that the rank of A is 2. So from this, of course, since we know that this is 2, we may look at all these properties and decide many things about A. For example, A is not invertible, right? This system, okay, we cannot now talk because we don't have B. Okay, we can find the dimension of this subspace, for example. We can find dimension of these subspaces and so on. Are there any questions about rank?
No questions.
No questions. What's the time now? I think we should start linear mappings next time. Okay. Okay, then. Thank you all who joined. See you next time.
Thank you.
Goodbye.
Goodbye.